So today's lecture is on the Perceptron convergence theorem. Right. Now, last class we were discussing about the least mean square algorithm, and generally it happens in most of the classes that even after the class we have some discussions continuing, some doubts cropping up. But surprisingly, for the least mean square algorithm lecture, I didn't have much of doubts from the students. So it's I hope that the last class was relatively less complicated as compared to things like VC dimensions and the shattering part of it. So I assume that the convergence criteria of the least mean square has been clearly understood, and we are now going in for the Perceptron convergence theorem, right? Basically, the theory part of it is more or less the same thing that we have been discussing for the past few lectures related to the single-layer perceptron. So the architecture that we are considering is, as before, an M input perceptron. So we were having a linear combiner that combines the inputs like this. So we are having the inputs as x1, x2 up to xm, and the associated weights we are calling as w1, w2 and wm, and this model, and in this model we are also adding the bias in the linear combiner directly. That means to say that we are having the input to be a fixed of a fixed value of +1 and having the weight w0 equal to the bias b. All right, so that effectively this is a linear combiner which, as you know, should add up all this w0 x0 in fact here is equal to 1 plus w1 x1, or in other words what we have been writing all the time, w transpose x or x transpose w, whatever way. Now this gives you basically the output v, and if this is the output v that we are getting after the presentation of the nth pattern input, then we write it as wtn xn, okay, where wtn is the transpose of the weight vector and xn is the input vector for the nth pattern that we are feeding. So this is what the v is, and then we are following it up with a hard limiter, where what this hard limiter do is that this v gets modified into phi v, okay, where the phi v will be transforming it into, hard limiting it into +1 or -1. So this is a hard limiter that will be used after that. So it is like a binary pattern classification that we are considering, that being the simplest case, and this is the output y that we are taking. So basically y is nothing but equal to phi v. Now this being the simplest kind of the architecture that we consider, we now attempt to solve a pattern classification problem, and let's say that we are solving a two-class problem, okay, in which case we have got existence of two classes C1 and C2, okay. So these are the classes that are linearly separable, okay. In fact, both these classes C1 and C2 will be existing in the multidimensional space actually. So although I am just drawing some representative diagram, but in general this is to be considered in a multidimensional sense. So let us say that this is a pattern that we are having C1, okay. So, supposing this one is the whole set of C1 that we have got, and let us say that we have got a set of C2. So supposing this is the set C1 and let us say that this is the set C2, Now, clearly the way I have drawn it, okay, makes it linearly separable. Okay, I think you can just get it, because what we can consider is that we can simply imagine that there is a line. I mean, although in this case I am showing it as a line, but actually it will be a hyperplane. That's correct. And can you tell me the equation of that hyperplane? Because we are in this case, I mean, the kind of model that we are using is that for V greater than or equal to 0, we will be having output equal to +1, and for V less than 0, we will be having the output to be equal to -1. So, if that is the case, then can you tell me that what is going to be the equation of this hyperplane? What is the equation of that hyperplane? You see, Vn is this. Vn is a scalar quantity, no doubt, but it is the dot product of these two vectors. That's very correct. So, here the decision boundary, because this hyperplane that we are imagining effectively is the decision boundary, right? And that decision boundary should lie at V is equal to 0. And what is the equation of V is equal to 0 in this case? Because we have to express it in terms of the W's and the X. So, that means to say that the equation of the hyperplane can be best written as W transpose dot X vector. Is it correct? So, this is the decision boundary. So, W transpose X vector is equal to 0. This is going to be the equation of the hyperplane of the decision boundary. Now, in this case it is very clearly linearly separable, but all cases are not linearly separable. I mean, simply you could take the problem like this. Let us say that this is our C1 and let us say that this is our C2. Okay. And in this case we certainly cannot find any hyperplane, okay, that separates the class C1 from class C2. Okay. So, the essential point that must be borne in mind is, of course, the linearly separable, the fact that we have been harping upon again and again. Now, again we are referring to a two-class classification problem. So, that means to say that the pattern set that we are having, okay, must be belonging either to the class C1 or to the class C2. So, you pick up any pattern, okay, any input vector x that we are going to pick up, okay, from the m dimensional space is either going to lie in C1 or in C2. And in order to train the system, okay, in order to train this perceptron, we have to take a set of patterns. So, when we take a set of patterns for training, naturally we have to derive the training set from both these classes. So, we have to train it with sufficient number of patterns taken out of the class C1 and sufficient number of patterns to be taken out of class C2. Okay. So, let us say that for the training purpose we take H1 as the training set which belongs to the class C1, okay, and H2 as the training set that belongs to class C2. So, effectively our training patterns that we are composing basically is the class H, which is nothing but the union of these classes H1 and H2, and H1 and H2 are the subsets of the actual class C1 and C2, because I mean certainly we are not taking every sample out of the space, we are only taking a subset of that. Okay, that is very clear. So, now that we are classifying it into a two-class problem, okay, then the classification equation we can simply write, given that the decision boundary is W transpose X vector equal to 0, we can definitely write that W transpose is X vector is greater than 0 for every X vector that belongs to the class C1. That means to say it is drawn from H1 set. Okay. And W transpose X vector is less than or equal to 0 for every X that belongs to C2. Okay. In fact, you can doubt the case of equal to 0, because where will we fit in equal to 0, whether we put it with the greater than sign or with the less than sign. I mean, we can put it in any one of them. In fact, equal to 0 is the boundary. So, whether you club it with the greater than case or club it with the less than case, that is something that you can arbitrarily do. So, this is essentially the classification that we want. So, that means to say that when we pick up an X vector from the class C1, okay, we would like to have that W transpose X should be greater than 0, right. If that is the case, we say that we have classified correctly. I mean, if we are knowing that X belongs to the class C1, okay, and if we have got W transpose X to be greater than 0, then obviously X will be classified into C1, which means to say it is a correct classification. But supposing we pick up X vector from the set H2, I mean, which normally belongs to the class C2. Okay. So, supposing we take X from the class H2, okay, from the set H2, then W transpose, then if we get W transpose X still greater than 0, supposing we get, that means to say it is correct or incorrect? It is incorrect classification, because if X belongs to the set C2, we should have got W transpose X to be less than or equal to 0. Okay. So, the classification that the network will ultimately do could be right, could be wrong. If it is wrong, then what we do? If it is wrong, then we need to update the weights. Okay. That means to say that if the after feeding the nth pattern, I find that the W transpose X is wrongly classifying the pattern, then I should update the weight so as to get a new Wn plus 1. But if I get a correct classification, okay, then what is it that I am going to do? Supposing I get a correct classification, I pick up X from the H1 set and I get W transpose X to be greater than 0, or I pick up X from H2 and I get W transpose X less than or equal to 0. What is the updating strategy that we are going to take? Huh? Keep the weights same. Keep the weights same. I mean, why are you after all going to disturb a correct thing? If somebody learns something correctly, okay, you are not going to teach him something more on that particular aspect. I mean, you can teach him something else, you can teach him a different pattern, but you cannot say that no, you have got it correct, but still you will have to relearn the thing. Okay. So, if that is the case, I mean, if you are already classifying it correctly, then do not update the weight. So, the weight updating algorithm that one can state could be, I mean, whatever I have just now talked of in the in language can now be just expressed in terms of equation as follows. So, the weight updating algorithm, we can say that let us take the nth member of the set, that means to say xn. So, we take the xnth vector, all right, as the pattern, as the input pattern. So, the updating rule says that Wn plus 1 is equal to Wn if W transpose xn is greater than 0 and x belongs to xn belongs to class C1. Okay. That means to say that it is greater than 0 and xn belongs to class C1 means that it is a correct or incorrect? Correct classification. It is following in line with this. So, we should have Wn plus 1 is equal to Wn, and likewise we should have Wn plus 1 equal to Wn if W transpose xn is less than or equal to 0 and xn belonging to class C2. That is very correct. So, these are the cases when correct classification is done, and very rightly we do not update the weight, we keep the weights as the same. Now, let us take the different case when the classification is wrong. So, as the second updating strategy, we should say that when the classification is wrong, then what we do? That means to say that if W transpose n xn is greater than 0 and xn belongs to C2, right? Xn belongs to C1 would have made it a correct classification, but I have purposefully made it an incorrect classification. So, I have drawn xn from C2, but I have got W transpose xn greater than 0. So, it is a misclassification, it is a wrong classification. So, wrong classification means we must necessarily update the weight. So, you tell me if that what should I write for Wn plus 1? I think by now we are knowing the weight update equation. Okay, so I think the students here, the viewers should attempt themselves. Should be Wn minus zeta. Yes, that is correct. So, it should be zeta xn, correct. So, it is the learning rate times eta times xn. Okay. So, that is so here we have to write Wn. Okay, I think if the font does not appear correctly, Wn plus 1 is equal to Wn minus eta xn, okay, if that is the case. And if we have W transpose n xn to be less than or equal to 0 and xn belonging to C1, that is also a misclassification. Okay. In this case, what should be my weight updating equation? Wn plus 1 is equal to Wn, correct. Why is it plus here and why is it minus here? Yes, yes, because we are moving in the direction opposite to the gradient. Okay. So, if we have, it is very clearly shown, by using this concept, if you find that the pattern belongs to C1, but you have got a C2. Why you have got C2? Maybe because your line or hyperplane actually is lying somewhere here. So, naturally you have to push it out. Okay. That means to say that you have to, in this case, okay, increase it, and in this case decrease it. So, that is in line with the direction opposite to the gradient, that we get minus here and we get plus here. So, now with this updating strategy, that means to say, again I repeat, that updating strategy here means that for correct classification no updating, for wrong classification just update according to the learning rule, this standard learning rule. All right. Now, based on this updating policy, we are now going in for the convergence theorem, okay, or the proof of convergence. Okay. So, we are now going in for a proof of convergence, but in order to just present the proof of convergence, okay, there are some initial assumptions that we are making. Okay. Do not think that these assumptions are directly going to affect the result. One assumption will affect the result surely, that you know that it is linearly separable class. Naturally, if that is violated, we cannot use the perceptron for pattern classification. So, the convergence must necessarily accept the linear separability as the essential criteria. But there are some extra things which are assumed for just for a simplified mathematical analysis, but we can see that if they are violated, or rather I would suggest that you can examine yourself that if the extra assumptions that we are making, if we violate that, that also will lead to a convergence, but maybe faster convergence, maybe slower convergence, whatever. But the kind of assumptions that we are making only for a guideline or only for the ease of computations are as follows. Okay. Number one is linear separability, which I think you all agree that we are definitely not going to violate. Okay. But other than that, we are going to have two more assumptions. One is that W0, okay, that means to say the weight vector that we are using initially is a 0 vector. Okay. So, we are starting with all weights to be equal to 0. Okay. In fact, it is not very wrong in assuming that, okay, simply because initially you do not have any clue. When are you feeding W0? Before feeding any pattern. So, you do not know that what sort of pattern you are going to feed, what the desired output will definitely be. There is no learning at all, it is just an initial assumption. Okay. So, initial assumption, I mean the weights, because the weights could be positive, because the weights could be negative. So, that is why we are taking it to be 0 vector, I mean nothing wrong. So, if we prove that for W0 equal to 0 vector, it is converging, means that again if we take any random value of W0, okay, it should also converge. Okay. So, that is one, and the second and the other assumption that we are making is that eta is equal to 1. Okay. Again this is for the ease of our analysis, and again eta is equal to 1, I should say that we are taking more like a, I mean conservative case, because you know, I mean by now you have already seen that when we take a smaller value of eta, the only price that we are paying for is that the time of speed of convergence is very slow. Okay. But the convergence is possibly more guaranteed for smaller. So, but in this case we are taking eta to be equal to 1. So, eta 1 is sufficiently high value of eta. In fact, normally we take the values of eta in the range of 0 and 1. So, if we are taking 1 and show that it is convergent for eta is equal to 1, then definitely there is no reason to believe that it is not convergent for lower eta values. Okay. In fact, I think mathematically also it can be very easily shown. I mean the approach that we are going to follow, you can yourself show that for smaller etas also this should be remaining valid. So, these two assumptions with which we are going to do the mathematical analysis are not any oversimplified assumption, or we are not losing the generality in any way by making these two assumptions. Okay. So, now let us see the that how do we arrive at the proof. Okay. Now, let us suppose that we keep on feeding the patterns xn, okay, and we start with n equal to 1, 2, etc. We keep on feeding the patterns, and initially let us say that it is doing misclassifications. So, to start with, we assume that it does misclassification when I feed x1, it does misclassification when I do x2, it does misclassification when I feed x3, but misclassification itself means that there is a learning. Learning is only there when there is error. Okay. So, you keep on doing misclassification, but if it is convergent, okay, then there should be some point, there should be some value of n where we are going to get a correct classification. Am I correct? So, if such value of n exists where the correct classification ultimately results, okay, then we can definitely say that the system is convergent. Okay. So, we are feeding xn with n equal to 1, 2, etc., and we assume that xn belongs to the subset H1. That means to say that it should be classified into C1. Okay. And we take eta is equal to unity in this case. Okay. So, that means to say that what will be our weight updating equation? We take eta equal to 1, and xn belonging to H1 pattern, okay, and we have got a misclassification. So, what should be my Wn plus 1 plus, yes. So, it should be Wn plus xn, because eta is equal to 1. So, it is simply Wn plus xn. Okay. Now, this is a very interesting form, and I have assumed W0 to be equal to 0. Okay. So, what is going to be W1? W1 is going to be, I mean, when n is equal to 0, so W1 will be equal to x1, x0, that is correct, x0. Okay. So, what is going to be W2? W2 is going to be W1 plus x of 1. So, that means to say that W2 will be equal to x1 plus x0, x1 plus x0. Okay. So, that means to say that Wn plus 1 is going to be equal to, yes. So, we can write it as x1 plus x2 plus so on up to xn, starting from x0, yeah, that is what is leading to, yeah, starting from x0, yes. Okay. So, this is simply a summation that we are getting for Wn plus 1. Okay. But again, another assumption that we are making, so we have made use of this assumption already. We have also made use of another assumption that W0 is equal to 0, and the third assumption that we are I mean we have started with is that C1 and C2 are linearly separable. Now, the basic fact that C1 and C2 are linearly separable means that although in this n pattern, so far we have assumed misclassification, although misclassification has occurred in this n, okay, but a solution definitely exists, isn't it? Because it is linearly separable, the solution exists, but only thing is that so far we have not reached that solution. Okay. So, the solution exists, and because the solution exists, we can find a solution. So, a solution W0 exists, a solution W0, here mind you I have put W as a suffix 0. So, it is different from W0. So, let us not make this confusion. So, it is, so here this is means W at the iteration 0. Okay. So, this is not what I am taking, here I am taking W0 means it is some solution, a solution W0 exists, okay, because they are linearly separable. So, a solution W0 exists for which we have W transpose, W naught transpose, yes, xn as greater than 0 for x1, x2, etc. up to xn, all these are vectors. So, x1 to xn, all of them belonging to H1. So, that means to say that a solution W0 definitely exists which does a correct classification, isn't it? Is it correct? So, that means to say that okay, now we can define a quantity. So, that means to say that for W0 transpose xn, okay, to be greater than 0, that means to say that there is some positive quantity alpha that we can find out for this value. So, there should be some value for which I mean we can find a minimum value, minimum positive quantity alpha which all these quantities, I mean W0 transpose xn, n equal to 1, 2, etc. Okay. Now, all of them should be greater than some positive quantity alpha, some minimum positive quantity alpha, all right. So, I define alpha as a minimum of W0 transpose xn, okay, and the minimum is defined over xn n equal to 1 to up to n here, xn belonging to H1. Okay. So, that is how alpha is defined. Okay. So, that means to say that if I now go back to this equation, Wn is equal to this. In fact, x0 we can take the initial pattern. I mean, in fact, there is as such no concept of x0 because x0 is not a feed. I mean, it is the initial state that you can take. Now, x1 onwards to xn that we are obtaining. Now, for all these things, I mean, for all these n terms that we have got, each of these n terms, okay, will be greater than alpha, isn't it? x1 will be greater than alpha, x2 will be greater than alpha, xn will be greater than alpha. So, that I can definitely put forward a case like this. I mean, supposing, okay, no, not x1 or x2, we will have to multiply it by a W transpose, yes. So, right. So, here let us say that this is equation number 1. So, what I am going to do is that I am going to multiply the equation 1, I mean I am going to pre-multiply. So, pre-multiplying equation 1 by W0 transpose, all right. So, what I am going to do in this equation, I am going to pre-multiply it, this you strike off. So, the W0 transpose Wn plus 1 is equal to W0 transpose x1 plus W0 transpose x2, so on up to W0 transpose xn. Now, individually, what is W0 transpose x1's limit? What is its bound? It must be greater than or equal to alpha. What is W0 transpose x2? That is also greater than or equal to alpha. So, what is the bound on W0 transpose Wn plus 1? Greater than or equal to NL plus, I mean greater than or equal to N alpha, yes. So, we can say that multiplying both the sides of equation by W0 transpose, W0 transpose Wn plus 1 is equal to W0 transpose, I mean I am just expanding the step, I mean in case you have not got the thing that I was talking about just now. So, our summation series would look like this, W0 transpose xn, and because individually all these terms are greater than or equal to alpha. So, that is why W0 transpose Wn plus 1, okay, is greater than or equal to N alpha, okay. And this, let us understand, is a very important bounding expression that we have got. So, I will call it as equation number 2, okay, which definitely gives us some limit about this W transpose, okay. And let us remember this result that we have got from this analysis. So, what is, yes please, any
Wn plus 1 there will be summation of xi from 0 to n.
0 to n, yes. So, I am not considering the case x0 because x0 is a trivial. My patterns are n patterns, I am starting with x1, okay. So, this is W transpose Wn plus 1 whose bound I have got to be greater than or equal to n alpha. So, this is the approach that I have got from where, I mean we have basically assumed a misclassification occurring for n number of times and shown that if that is the case, then W0 transpose Wn plus 1 must be greater than or equal to n alpha. Now, there is another route by which we can try to attempt the bound. Okay, before we go in for that, okay, let me also discuss more on this. So, this is a very interesting bound that we have got. Now, on this equation 2, if we apply the Cauchy-Schwarz inequality, if we apply the Cauchy-Schwarz inequality, then you see on the left hand side of it, we are having W0 transpose Wn plus 1, all right, which is a I mean which is itself a dot product, a scalar quantity, and going by the Cauchy-Schwarz inequality, we should say that if we individually take the norms of these two vectors, if we take the squared norms of W0 transpose and Wn plus 1, and if those squared norms are multiplied together, then that should be greater than or equal to the W0 transpose W, this dot product that you are getting, square norm of that, okay, square of that rather. Okay. So, in other words, by using Cauchy-Schwarz inequality, we can write norm of W0 square times norm of Wn plus 1 square is greater than or equal to this quantity, this being a scalar quantity W0 transpose Wn plus 1. So, it is W0 transpose Wn plus 1, all right, this square. So, this is Cauchy-Schwarz inequality, and we know the bound on W0 transpose Wn plus 1. What is that? That is greater than or equal to n alpha. I mean this term is greater than or equal to n alpha, means this square term is greater than or equal to n square alpha square. So, we can definitely write W0 square Wn plus 1 norm square is greater than or equal to n square alpha square, correct. So, that now we can get Wn plus 1 norm square to be greater than or equal to n square alpha square by norm of W0 square. Is it correct? Pretty simple. So, this is what we have got as a bound for Wn plus 1, because ultimately that is what we are looking for, isn't it, that what is going to be the bound on this Wn plus 1, and just see as if it is going to suggest something very alarming. That means to say that we keep on increasing n, okay, supposing we keep on increasing n, that means to say that the weights will keep on increasing in magnitude and exponentially. I mean it is basically n square, and it must be greater than or equal to this. So, this is something to feel alarmed of. So, we were thinking of showing convergence, but are we really going in for a convergence like this? Okay. But okay, we have got this expression correct, and let us remember this, that we have got an equation 3 which we treated as an alarming equation, and now let us take a second development route, an alternative route that we explore. So, the alternative route we take as follows. Again we consider a series of misclassifications to start with, right. So, we take that Wk plus 1 is equal to Wk plus x of k for k equal to 1 to n and xk belonging to what? You are not attentive. Belonging to H1. I mean this is basically the misclassificational update. I mean same thing that we had written last time also, isn't it? Last time also we began with this. So, there is nothing new that I have written, only thing is that I just put the index to be k, k is equal to 1 to n, and xk belonging to H1, but there is a misclassification. Because this there is a misclassification, that is why I could write that. Now, in the earlier case what I did? Earlier case I iteratively took, I mean k is equal to 1, 2, etc., I kept on taking. Okay. In fact, one of the things that we did little wrong is, okay, we took k is equal to, okay, W0 we started with, but ultimately the patterns are k is equal to 1 to n that we are feeding. Anyway, so here instead of going in that iterative way that we first compute W1, then compute W2, then compute W3, and then expressing the last Wn plus 1, which we have already done and seen. Okay. Instead of doing that, let us take this equation on its own and let us obtain the squared Euclidean norm of both these sides. So, take squared Euclidean norm of both the sides. Easy. What you are going to do is, the left hand side you are going to multiply by W transpose k plus 1, the right hand side you are going to multiply by, pre-multiply by Wk plus xk whole thing transpose, or rather to say Wk transpose, I mean W transpose k plus x transpose k, you are going to pre-multiply with that. So, you know what you are going to get. So, we can directly express it. I think that we need not have to expand it. If you have doubts, please do not hesitate to ask me. Wk plus 1 is going to be equal to Wk square, okay, plus, yes, please go on, xk norm square plus twice, correct, twice Wk transpose dot xk, correct, very correct. Now, we are assuming that the perceptron incorrectly classifies. So, our basic assumption is that perceptron incorrectly classifies for k equal to 1 to n. So, because it incorrectly classifies, what can we say about this Wk transpose xk? Less than 0, yes, less than 0. So, W transpose k xk is less than 0. So, if W transpose k, if W transpose k xk is less than 0, in that case what can we say about the relationship between the left hand side and the first two terms of the right hand side? Smaller than that, definitely, because Wk xk is less than 0, that is why it is subtracting from what I have got as Wk xk. So, definitely Wk plus 1 should be less than or equal to, Wk plus 1 norm square should be less than or equal to this square plus this square. So, we can definitely write, because misclassification has happened, we can definitely write that Wk plus 1 square is less than or equal to Wk square plus xk square, right? Or equivalently we can say that Wk plus 1 square minus Wk square is less than or equal to xk square. Now, this is a very interesting expression. You see, now we are going to apply this equation, okay, we are going to just apply this inequation rather for k is equal to 1, 2, etc. You put k is equal to 1, what you get? W2 square minus W1 square less than or equal to x1 square. You take k is equal to 2, what do we get? W3 square minus W2 square less than or equal to x2 square. Add them together. Okay. So, you have x2 square here minus x2 square there, all cancelling out. It is only the last term minus the first term that you are going to get. And okay, if you are taking initial weight assumption W0 is equal to 0. So, definitely that finally leads to the fact that if we go on iterating this, then Wk plus 1 square, okay, that should be less than or equal to summation of xk square, where we sum up for k is equal to 1 to n. Okay. W 0 square is in this case 0 because k is equal to, yes, I mean always we land up in a, this index 0 is always a problem. Yeah, if we go on for k is equal to 0 1 etc., yeah, but the pattern is not fade for k is equal to 0. So that is why for the pattern we sum for k is equal to 1 to n, but yeah, take that as 0. So here we are getting w 0 square to be equal to, w 0 square is equal to 0. So here we can write that w k plus 1 square is equal to summation x k square. Okay. And this is something that we can tell that here w k plus 1 is definitely less than or equal to, here less than or equal to this quantity. So which means that if we define, yes, any doubts? W n plus 1, yeah, you are right, w n plus 1, why am I writing k plus 1, very correct, thank you for pointing out. So w n plus 1 square, so I mean we have already got one expression of w n plus 1, mind you, we, I mean remember this, and now we are going to get something new over here, and one new thing that we are getting is, earlier it was greater than or equal to something, whereas here it is less than or equal to something, and something how conveniently we can express. So let us define a positive quantity, I mean norm of x square is definitely going to be positive, isn't it? So let us define beta as a positive quantity which is going to be the maximum of this xk square. Okay. And where do we define xk? This xk all belong to the space H1. Okay. So xk is picked up from the space H1 and we are taking maximum value of that as beta. If we take the maximum value of this to be equal to beta, then naturally x1 square is going to be less than or equal to beta, x2 square less than or equal to beta, like every xk square is going to be less than or equal to beta. So that in effect, what is the bound that we are getting on w n plus 1 square? Less than or equal to n beta, yes. So what we are getting is that w n plus 1 square, okay, is less than or equal to n beta, okay, and let us call this as equation number 4. So we have got equation number 3 and we have got equation number 4. The interesting observation is that equation number 4 puts a bound which says very interesting thing, that w n plus 1, I mean as you increase n, okay, the w n plus 1 square is linearly decreasing. I mean you, I mean not that, I mean it is linearly increasing with n. I mean its bound is, I mean it is going to be less than or equal to n beta. So it is specifying a lower limit according to equation 4, and according to equation 3 it is specifying an, no, it is, sorry, other way, it is specifying a lower limit from equation 3 and it is specifying an upper limit from equation 4. And is it going to be, I mean this equation number 3 and equation number 4, these two that I have shown, okay, are they going to be consistent for very large value of n, let us say? It will be impossible to satisfy both equation 3 and 4 simultaneously at very large value of n, because at very large value of n this lower bound is going to be very high, whereas the upper bound is going to be low. So that is why we must have some point, okay, at which, I mean which is the limiting case that both 3 and 4 get satisfied. And let us say that there is some n which we can say that n equal to n max, n equal to n max, okay, at which both 3 and 4 are satisfied with equality sign. Okay. So, that means to say that n max is the solution of what? Let us again have a look at this. So, we must put n max in place of n over here. So, here this leads to n max square alpha square by W 0 square, and that should be equal to n max times beta. So, we must have n max square alpha square by W naught square, okay, equal to n max times beta, if we satisfy both 3 and 4 at the point n equal to n max with the equality sign. Okay. So, from here we can obtain the limit on the n max. Okay. So, we obtain what? So, we obtain here that n max is going to be equal to beta W 0 square by alpha square. Okay. This is the limiting value of n. So, that means to say that after this n is reached, okay, or this is the upper limit on this n, okay, beyond which there will not be any further updating of the weight, meaning that by the point n equal to n max, okay, we have achieved a correct classification. We began with incorrect classification, and at n equal to n max, or maybe earlier than that also, okay, we are going to have a situation where the incorrect classification will be replaced by a correct classification, and that is the convergence that we are aiming for. So, that means to say that the perceptron, so this is called as the fixed increment convergence theorem. Beta, no, here see we are satisfying 3 and 4 simultaneously. Yeah. So, 3 and 4 can be only satisfied up to a limiting value of n, okay, and that is what we are taking it to be n max. Now, we just state this fixed increment convergence theorem. Okay. Now, what it says is that we have some n0 which is less than or equal to n max. N max is an upper bound that we have got, but we have got n0 less than or equal to n max, for which we have W n0 equal to W n0 plus 1 equal to W n0 plus 2, so on. Okay. So, this is ultimately the solution vector. So, here all these are equal means it is a convergence, it has reached a convergence, all right. So, that is what for today, because we are running short of time. The convergence theorem aspect more or less we have covered, okay. Just one or two small items remaining to that, and then we are going to take up another very interesting case where we will be taking up the classical, one of the classical classifiers, which is the Bayes classifier, and we are going to show a relationship and an interesting relationship between the Bayes classifier and the perceptron. That will be in the coming class. Thank you very much.